Hi, this is Mrs. Ward reading the chemistry book, chapter 11, section 2, Mass and the Mole. The objectives of this section are to relate the mass of an atom to the mass of a mole of atoms. Okay, remember, mole is a number, it's a counting number of atoms. To calculate the number of moles in a given mass of an element and the mass of a given number of moles of an element. To calculate the number of moles of an element when given the number of atoms of the element, and to calculate the number of atoms of an element when given the number of moles of the element. Okay, so molar mass is the vocabulary. So it looks like a lot of math, a lot of calculations again in this section. And we're going to use some of the equations that you've used in the past where we're paying attention to how we put our conversions, how we list them, so that in the end, the unit that we want in the end ends up on top and uncanceled. Okay, so we'll be doing that throughout this section. You wouldn't expect a dozen limes to have the same mass as a dozen eggs. Dozen, remember, is 12 items. Eggs and limes differ in size and composition, so it's not surprising that they have different masses, as figure 11-3 shows. Okay, 12 limes, 12 eggs, different mass. Moles of substances also have different masses for the same reason. The substances have different compositions. If you put a mole of carbon on a balance beside a mole of metallic copper, you would see a difference in mass, just as you do for a dozen eggs and a dozen limes. Carbon atoms differ from copper atoms. Thus, the mass of 6.02 times 10 to the 23rd atoms of carbon does not equal the mass of 6.02 times 10 to the 23rd atoms of copper, right? This is a mole, right? 1 mole of carbon does not equal the same mass as a mole of copper. How do you determine the mass of a mole? In the mass of a mole, in chapter 4 you learned that the relative scale of atomic masses uses the isotope carbon-12 as the standard. So every other mass is going to be compared to carbon-12. Each atom of carbon-12 has a mass of 12 atomic mass units, AMU. This is the unit of measurement for the mass of atoms, okay? And carbon-12 has a mass of 12. So everything else is, every other mass of an atom is relative or related to the mass of carbon-12. The atomic masses of all the other elements are established relative to carbon-12. For example, an atom of hydrogen, 1, has a mass of 1 AMU, atomic mass unit. The mass of an atom of helium, 4, is 4 AMU. Therefore, the mass of one atom of hydrogen is, hydrogen 1, is 1/12 the mass of one atom of carbon-12. Okay, because they're related to each other. Because 1 is the same as 1/12 of a carbon-12 atom. The mass of one atom of helium-4 is 1/3 the mass of one atom of carbon-12, or 4/12, right, which is the same as 1/3. You can find the atomic masses on the periodic table, but notice the values shown are not exact integers, right? They're decimals. For example, you'll find 12.001 AMU for carbon and 1.008 AMU for hydrogen and 4.003 AMU for helium. These differences occur because the recorded values are weighted averages of the masses of all the naturally occurring isotopes of each element. Okay, in other words, they do math, they do averaging and weighting them in order to come up with this, which is why they're not exactly whole integers but decimals. How does the mass of one atom relate to the mass of a mole of that atom? So not one, but 6.02 times 10 to the 23 of those atoms. You know that the mole is defined as the number of representative particles or carbon-12 atoms in exactly 12 grams of pure carbon-12. Okay, again, so both AMUs and moles are related to pure carbon-12, okay? Thus, the mass of 1 mole of carbon-12 atoms is 12 grams. What about other elements? Whether you are considering a single atom or Avogadro's number of atoms, a mole, the masses of all atoms are established relative to the mass of carbon-12. So we put them in relationship to carbon-12. The mass of a mole of hydrogen-1 is 1/12 the mass of a mole of carbon-12 atoms, or 1 gram. The mass of a mole of helium-4 atoms is 1/3 the mass of a mole of carbon-12 atoms, or 4/12, which makes it 1/3, right? Or 4.0 grams. The mass in grams of 1 mole of any pure substance is called its molar mass. The molar mass of any element is numerically equal to its atomic mass and has the units grams per mole. Okay, grams per mole. An atom of manganese has an atomic mass of 54.94 AMU. Therefore, the molar mass of manganese is 54.94 grams per mole. When you measure 54.94 grams of manganese on a balance, you indirectly are counting 6.02 times 10 to the 23rd atoms of manganese, okay? So you can count how many atoms by measuring it on a balance, okay? So when you measure mass, you can figure out the counting of the atoms as well. Figure 11-4 shows the relationship between molar mass and 1 mole of an element. The problem-solving lab will further clarify these relationships. So here is a mole of manganese, okay? And its mass, when we put it here, its mass is equal to its atomic mass that we find on the periodic table in grams per mole, okay? All of the elements are the same in that way. They don't all have the same mass, but their atomic mass matches the mass of 1 mole.